I mean, we should say, oh, you had like for the or something. Is it related? Like, it's related. Some like, oh, you know, is it the modules like a? I don't know them either.
Think it starts?
Yeah.
We really make sure we have money.
Well, if you don't have money, then I guess
Can I get a green lights?
well, we have to.
Or can I get someone to announce?
Just start.
3,
Sorry.
2.
Okay. Hello. Not sure what the regulars are. It's at least that's going to be linear algebra. So raise your hand if you know linear algebra. Not all people have raised their hands. So I'm going to first give a warm up on linear algebra. I will not be hearing any allegations of hiring paid actors to not raise their hands.
You speak up.
Yeah. Thank you. Okay. So what is the symplectic vector space? So suppose you have a real vector space, bidimensional, and you want to understand what it means for V to have a symplectic structure. So there are two equivalent ways. I mean, okay, I should go quickly through this because it's just basic. Most people already know. So omega a form of R is a symplectic form if so we can write this in three omega is bilinear. Two, omega is alternating. That is, if you take any two vectors, VW of V, you'll get this alternating property. And the third requirement is that omega is non-degenerate. What does it mean? It means V is a finite dimensional real vector space. You can choose some basis, and then this bilinear form will just turn into an n by n matrix. Right? So we just require that this matrix is non-degenerate. It has non-zero determinants. Okay, that's one description. Then there's also another description, which passes from omega to the so-called, it's sometimes denoted omega sharp, and it's now a map from V to V star, the space of linear functionals on V. I mean, how do we obtain this this omega sharp from omega? We just said omega sharp of V. So V is a vector in V. Now this should be a linear functional on V. We just said this linear functional to evaluate on W as omega of VW. Yeah. So how do these properties translate into this? I mean, the first of them is just the linearity. well, it's the linearity of omega sharp and the very fact that its target is space of linear functions. It's kind of in the definition already. This alternating property translates into omega sharp being skewer joints. That is, if you take the adjoints of omega's sharp, you'll get minus omega sharp. What does it mean to take the adjoints? It's an operator from V to V star. Take the adjoint, it maps from the dual of this, which is V, again, to the dual of this, which is V star. So both of these operators are from V to V star. And you're saying one of them is minus the other. And the third one is now this non-degeneracy just translates into the fact, which is the most useful about this thing. And why this is the reason for introducing it in the first place, is non-degenerate. Omega sharp is non-degenerate means it's an isomorphic. It's inverted. Okay, that's good, but why am I telling you this? I mean, you're not going to understand why I'm telling you this until some point. But what's useful thing we can infer from these properties is we can talk about isotropic subspaces of B with respect to omega. So a subspace L of B is isotropic if you restrict the form omega to L, you just get the zero form. In other words, omega of VW is equal to zero if B and W both belong to L. Okay, so that's what it means to be an isotropic subspace. The property that I want to emphasize is that, and we have stated this proposition. If L B is isotropic, then the dimension of L is controlled.
Can you just give us an example of was it a symplectic form on just some
Yes.
the vector space?
Yeah. Let's say I just finished the sentence. Then the dimension of L is controlled by half the dimension of B. Yeah, what's some examples of the symplectic vector space? So the most basic example, which does not really reflect the properties of symplectic vector space, but it's kind of too trivial. But the most basic example is you can take B to be a plane. And you can take omega to be the form, the volume form on the plane, dx dy. Okay, what it means is that if you have two vectors v and w, you need to span a parallelogram by them, and the volume of this parallelogram is going to be omega of vw, except it's the oriented volume. If you, it's only positive if v and w are in the right orientation, and if you swap them, the sign will change. Okay, what this means is that if you have two vectors with coordinates v1, 2, and w with coordinates w1, w2, then this omega of vw will evaluate as v1, w1, w2 minus v2, w1. And we take the x component of this, multiply by the y component of this, and then you alternate. That's why I write wedge there. Okay. In general, you can, well, nobody will mind if I write here. Sure. In general, you can just generalize this and put v to be equal to r2n, and set omega to be dx1 wedge dy1 plus dx2 wedge dy2 plus dxn wedge dyn. Where, of course, I'm saying that dxi and dyi are coordinate functions on R2n. Okay, so this has the matrix form of is ones on the diagonal, and this block is 0, this block is 0, and in this block there are minus ones. You can see how it's skew adjoint. This is the standard form of a symplectic form. In fact, any symplectic form and any real symplectic space can be put in this form. In particular, any symplectic vector space of the real numbers is even dimension.
What is that matrix?
Can you see?
Yeah. What does it represent?
It represents this form in the basis, the standard basis. So the first vectors correspond to the x's, and the last vectors correspond to the y's. So here's dx1, dy1. Okay. I wonder how much time. Okay, proposition. And how do we prove this proposition? Well, we can just say if L is isotropic, we can notice. Then L is contained in its own orthogonal complement with respect to omega. Because if you pair any vector of L with any other vector of L, you'll get 0. The orthogonal complement consists precisely of all vectors that pair with all vectors from L by 0. Yeah. Therefore, we can see that, I mean, the dimension of this orthogonal complements is equal to the dimension of V minus the dimension of L, because the form is non-degenerate. I'm not explaining this. Okay, and then from this, you see this, put this to the other side. Yeah. So this was the linear algebraic form. Now it's taken 20 minutes. Let's not talk about this. So okay, so what about part 2 of the 4 or 5? This is part 1.
Okay, part is older. How many parts is
Yeah, 4 or 5.
Anyway, so let M now be a smooth manifold.
I'm going to define a trivial object, J0 of M is what's also called the space or the bundle of 0 jets on M. It's just the trivial bundle M cross the real line. Okay, why am I doing this? Well, some reason. So now I want to say that for any function f on M, I have its graph, which is a section of this bundle, which is the image of the section of this bundle. Okay, let me say something more precise. There is a corresponding section J0 of F of the 0 jet bundle, which is just defined as sending a point X to something here, right? I'm just going to send it to X, F of X. Okay, then I can call the image of this section is I can call it the graph of okay, this is kind of trivial to mention. It would be more interesting if we were working with a non-trivial bundle. In general, if you have a vector bundle, you can define jets on this bundle, and then this bundle will just replace this. Anyway, okay, these were the 0 jets. Why am I defining 0 jets? Is because what I really want is to try to access the infinitesimal first order information about functions in this case geometrically. Okay, so imagine a function choose this graph. Okay, and I want to look at the tangent elements to this function, tangent hyperplanes. So I'm going to define x. U is going to be the coordinates on J0M. Coordinates. We can write XU to be points in the zero-jet space. Anyway, how am I going to treat this thing geometrically? This is where the one jets come in. But first, I need to define what it means to be a contact element of space. Okay. So definition: if N is a smooth manifold, a contact element on N is a tangent hyperplane theta in some, a hyperplane. What does it mean to be a tangent hyperplane? It's a linear subspace of some tangent space to N, okay, at some point, which is a hyperplane that it explains itself at some point. Okay. Now, on this particular manifold, where our graph belongs, okay, there's a specific direction, which is the vertical direction. That gives us a canonical rank 1 tangent distribution. We're going to make use of that, define only a certain subset of all contact elements on this manifold. So I guess it's also a definition. A tangent, well, that's contact element. So a contact elements theta in some tangent space to J0 of M, right? Now the points of J0M are indexed by two things: a point in M and a number. So it is called non-singular if it does not contain the vertical line. This vertical line is also spanned by the vector dd. The line, the u axis. Okay. So now we can, why are we looking at non-singular tangent, non-singular contact elements? Because for a graph of a function, all of its tangent hyperplanes are non-singular. A function cannot have a tangent hyperplane which contains the vertical line. Right? It's always something that does not vertical line. Okay. Another definition then is that J1 of M, now it is the space of one jets. Of of, but M is the space of all non-singular contact elements on M. So we're just taking on the zero jet space. We're just taking all the non-singular contact elements on this jet space. We're putting them together. We're calling this the one jet space. You notice how geometric this is because we haven't used any analytic expressions in any coordinates yet. Okay. Yeah.
How do we arrange these do we just take like a disjoint union of all like the singular contacts?
Trivial, like it's trivial.
Well, you can, yeah, okay. So the space of all hyperplanes in the tangent bundle of a manifold is a bundle over the tangent bundle with fiber. Sorry, it's a bundle over the manifold itself with fiber a projective space, because the space of all hyperplanes in a certain space is a projective space. It's the projectivization of the cotangent bundle. So you have a natural topology on this induced from that structure of the projectivization of a tangent bundle, of the cotangent bundle. But I'll also define coordinates here, and it will turn into a manifold actually. So it's not. So it's fine. Okay. But I will note that this space of one jets is, or let's say, has a projection of pi from J1 M to J0 M. Because after all, this is the space of all contact elements, non-singular contact elements in J0 M. So if we have a non-zero contact elements, non-singular contact element in J0 M, we just look at the points at which it is a contact element. Okay. If it's a tangent hyperplane at some point, we just take that point. Okay. So now what about the coordinate expressions? I will notice that any non-singular contact element contact element is actually a graph of a linear function, linear functional, right? A hyperplane that does not intersect the vertical line is uniquely given as a graph of some linear functional. That is, you can just write the equation du, let's say this theta is the solution of the equation du. It's a linear equation. Du is equal to p bx. So this p is a linear function on the tangent space. I'm just saying it's like writing y is equal to ax. Is this clear?
Like this is the fiber, or like we should understand this as a
bundle, right? J bundle.
Yes, but this is just one contact element.
You're writing down the fiber at the right.
Sure. I'm saying theta is a subspace of the tangent space to J0, right? To the space of one jets. The tangent space to J0 itself, the tangent space to M cross a line. So now I'm just writing down a linear function on the tangent space to M. I'm saying, let's take its graph, okay? Here. Then this graph is a tangent hyperplane, which does not contain the vertical line.
Yeah, sure.
And
Sorry, what is this with respect to J1 of M?
this is so this gives us a map of bundles. In fact, from J1 of M to the cotangent bundle of M, which just takes a contact element and basically takes its slope, which is a linear functional here. But
So wait, are we viewing the tangent bundle as like the tangent bundle of the trivial bundle? Sorry, like the
when I'm writing T star M means the cotangent bundle of M. I'm writing tangent bundle of something, it means the tangent bundle of that.
It's going on like the
we have like this we have this zero jet, which is a trivial bundle. And then we also have these images of these sections. It's also like a submanifold.
There are submanifolds in the total space of the bundle, yes.
So are we considering the contact elements to live as subs like hyperplanes in respect to the total space, or respect to
so there are contact elements in J0 of M, which means by this definition they're tangent to J0 of M. And you can see it here, right? That these are not they're not tangent to the line itself. They're tangent the tangent lines at the plane itself, not.
but like they don't have to like be tangent to this graph. They can not necessarily.
Yeah, I mean, here we're considering all contact elements, but any graph gives us a natural collection of contact elements.
Okay.
That I'm going to work with right now.
But we should think of that as a bundle.
You should think of this as a bundle. It's a bundle over this bundle. So we actually
Yeah.
a tower of bundles, J0M to J1M to J0M to M. And there's also the cotangent bundle of M, and J0M maps to it, but this is not, this itself is not a bundle. So these are bundles.
Yeah.
This, well, actually this, but that's not, it's not worried about this whole collection thing. Actually, you can, this tower suggests that you can extend this further. It's true. I'm only talking about one jet here, but you can define further jets, and you can define infinity jets as the projective limit of this tower.
I mean, it's not that much more complicated than to just take
Yeah.
derivatives.
You will be taking, instead of contact elements, which are the tangent hyperplanes, you'll be taking tangent graphs. So here you're taking graphs of linear functionals. Then you'll be taking graphs of quadratic functionals.
So not the higher derivatives, but
From the analytic point of view, that will correspond to high derivatives. Actually, that will correspond to taking the Taylor polynomial of your function up to some order. So this is giving you a geometric axis to geometric counterpart to working with derivatives. Okay. Where's the time? Good. 20 minutes. Okay. It's not ideal. Okay. So now, as suggested by that picture, I will define. So here I had defined the zero jets of functions. Here I will define one jets of functions. Yeah, it didn't mention. I'll refer to points of J1 of M. As triples X, U. Those are just coordinates from J0. But now I also have this contact element. Refer to them as triples. In fact, I can also refer to them as XUP, where P is this slope, but I refer to them using beta. Okay, so the one jets J1 of F is the map sending. It's a section of the one jet bundle. So it's the map sending X to the triple X, F of X. Yes, it's here. But the new coordinates will be, let's call this theta X of F, where this theta X of F is the tangents elements to the graph. Okay? So I can write it as the tangent space to the graph at the points X, F of X. Right? And the graph is scheme of J0 lives inside the whole tangent space of the zero jet bundle. So it is, and it is a hyperplane, so it gives us a contact element. Okay, so now I'm taking a function f, and not only graphing its values, I'm also graphing its tangent planes, or in other words, I'm just graphing its first derivative. Okay. So this is a good place to define the coordinates on the one jet bundle, and also see how this one jet thing looks in coordinates. So just from this perspective, we can see that if x1, xn are coordinates on M local, then there are corresponding coordinates on the one jet bundle. x1 to xn. Then there's u, which is just a real number. And then there's p1 to pn, where if I change coordinates, these last coordinates will change like cotangents, like a cotangent vector, because they literally are a cotangent. This map actually splits. In fact, this whole bundle splits into this bundle plus this trivial part q. So anyway, these are our local coordinates, and this expression of the one jet of f in these coordinates is just the thing sending x to the point with coordinates x1, xn. Then there's f of x, and then there's these p's, which are supposed to be the slopes of the tangent hyperplane to the graph. So they're just given by the derivatives. The derivative is the slope of the tangent graph, of the slope of the graph at a certain point. Okay.
Then I'll be some like dxi's. Oh wait, this is
dx.
This is just in coordinates. This is yeah, no, never mind.
So you can see how this one jet contains the infinitesimal information about f. It's the first order information about f, even though one jet. So what we can notice immediately is that this one jet of any function satisfies a lot of constraints. Obviously, because its target has much greater dimension than its source, but this in particular satisfies the equation that these coordinates are literally the derivatives of this coordinates with respect to their class. So
So what's G1 of x again?
first jet. German. Oh.
Yeah.
So this function satisfies that this pi, this coordinate, is the derivative of this coordinate with respect to certain coordinates. In fact, if you do a bit of chain rule applications and stuff, basically, you can imagine multiplying both sides by dxi or something. I won't be doing the whole computation here. It's short, but it's confusing. But in fact, this condition translates into the fact that J1 of f is in the kernel of a certain one form. In other words, if you pull this one form back by this map, you get 0. What is alpha? Alpha is du minus p dx, where this means du minus the sum pi dxi. Okay, so I hope you see the resemblance, but in fact, these equations are equivalent to this. this. The questions about this? Thoughts?
About the x1 to the xn.
Yeah, I mean, obviously they satisfy the equation that x1 is equal to x1, right?
So that's trivial.
That's, yeah, I mean, we're not mentioning that equation because it's not interest. But yeah, it's true that this satisfies, of course, this satisfies many constraints, as I've said, but this is the most interesting one, or actually it's n constraints for each coordinate. And we'll be working with this form, alpha. Maybe, well, that depends. We'll be working with it for 1 minute.
Keep going, keep going. Locked in.
Okay. So this form alpha is of main interest here. Why? I mean, this is what's called the contact form on the space of one jets. So it's good that I at least got to this part. The word contact is not completely clickbait in the title. Anyway, yeah, actually I'm stalling because I don't remember what's the next part. Let's go. Okay. So
Yeah, it's not hard. Okay, it's not abstract nonsense.
now what I want to say is even this condition, which is actually it's phrased in terms of coordinates, right? So you might wonder what happens if we change the coordinate. This one form alpha is only defined on a certain coordinate patch of J1 with M, right? Alpha is one form on the total space, but only locally. So the question is whether if you change coordinates, it will not, will it glue or not? Actually, if you just check, the form alpha glues nicely. It changes like a one form if you change the coordinates on M. So you do get, just using this expression, you already get a global one form on M. And then you can work with it as a canonical object. But there's a better way to define this form as a global canonical object, which is geometric. So you'll see that this condition is just tautological if you look at it geometrically. It's kind of the main idea of this talk so far. I know. So yeah, the distribution of kernels of alpha, right? At every point, alpha is a one form. It's not zero everywhere. So its kernel is a hyperplane in J1 of them. To get the distribution of hyperplanes. At every point, you have a tangent hyperplane. On J1 of M is called the Cartan distribution on the space of one jet bundles on M. Green. What's the space of one? On the one jet space. Okay. So what I'm proposing is that we can define this distribution geometrically. So geometrically. You have your projection from J1 of M to J0 M, which was defined there. And you can do the following. You can define the hyperplane, let's call it L, at X, Q, theta, a point here. So this will be a tangent hyperplane at this point, as just the pre-image of theta itself. So it can be confusing, but theta as a coordinate is itself a contact element in J0 of M, but is a hyperplane, a tangent hyperplane in J0 of M. So if I take its pre-image, I meant to write this guy. You need to take the pre-image under the differential of pi. Okay, the differential of pi projects the tangent space of this to the tangent space of this, and theta is a hyperplane in the tangent space of this. So its pre-image is a tangent plane, the tangent hyperplane in the tangent space of this. So this here is theta, okay, in Tx q of J0 of M. Here I have my tangent space at x u theta to J1 of M. So I'm taking, and there's this projection pi star. Okay, I'm just taking the pre-image of this. Of this hyperplane. It gives me a hyperplane here. Okay. So my claim is that this distribution of hyperplanes is the Cartan distribution. You can verify it in coordinates. It's I had more time.
But you don't actually need to do this. There's a short set sequence where from Jm to Jm minus 1 always, and the kernel is always going to be some symmetric power of the cotangent one.
Yeah, this
This is a
it's something that's
Exactly.
takes
We're doing geometrically. Okay.
some time to
sequence of vector bundle.
all right. So we get some distribution. In fact, okay, you can verify that it is the same distribution, but this property that the one jet of any function integrates this distribution becomes integrating a distribution means that your submanifold is everywhere tangent to the distribution. So the property that the one jet of that integrates this distribution becomes tautological, because for any function f on M, you have the one jet of f projected to the zero jet space, exactly being the zero jet of f, correct? So if I take the tangents, okay. Now I remember that J1 of f at a certain point is x f of x theta x of f. And I remember that this is xu. And that's this hyperplane theta here is exactly this hyperplane theta x of f. So what I'll be taking here is L x f of x theta x of f. By this definition, it will exactly be pi star inverse of theta x of f. But this is exactly the tangent space to the graph of f. So if I can draw a picture. So just as here, have the graph of f, have this contact element, which is exactly theta x beta. But then the one jet is simply the graph of f, but lifted further to the one jet space. Projects onto this graph of f. So of course, the tangent space to the lifted graph of f then projects onto the tangent space to the non-lifted graph of f. Because of this. Okay, so this verifies the fact that the one jet of M integrate the Cartan distribution geometrically. I fear that this should conclude the whole talk because I don't have time. I covered this page, but not this.
Oh, we did all that deflecting nonsense for nothing?
Well, it was supposed to not be for nothing. Yeah, but currently it doesn't seem like a good idea to continue because
Oh, yeah. Very good, very good.
yeah, I would have talked about how this applies to differential equations, how you can actually solve.
That's fine. Yeah, we don't need to know that.
This doesn't make any sense. Like it doesn't make sense to define all this.
Wait, can I solve differential equations by considering things like geometric jet bundles instead?
Yes, and the most important or the most the best application